Hello, I'm Maria Villaris. I'm a quantum physicist, and I thought it would be fun to do a video responding to the recent announcement from Google about their new quantum chip, which has generated lots of excitement and publicity for the field of quantum computing in the last couple of days. So let's have a look at the Google blog post about the announcement. And just to introduce my own background, I um I recently finished my PhD in the foundations of quantum information science at the University of Oxford, and I now work at the quantum computing company Oxford Quantum Circuits as a developer advocate, partly doing quantum error correction research and partly doing technical science communication. And I've also previously worked on quantum education with IBM Quantum and before that with the quantum software company Riverlane. So I started following the field of quantum computing around summer 2019. And then in October 2019, there was an announcement from Google of having achieved a milestone called quantum supremacy. And what this milestone meant was that they claimed to have been able to run a certain computation in such a way that it was much more efficient on a quantum computer than on a classical computer, and it would take a very long time on a classical computer, longer than is feasible to do. And that announcement caused lots of excitement at the time, back in autumn 2019. And so it's interesting to compare to now, 5 years later, what's different and what's happened since then. So, to give you a summary of what happened, is that there was this milestone reached. It wasn't a claim of having run a useful computation faster on a quantum computer than a classical one, just some kind of computation. And then there's always this race against classical computers because a short while later, companies like IBM were saying, look, you can actually solve that problem efficiently on a classical computer using a certain simulation method. And then you have this kind of constant back and forth where these demonstrations of what people call quantum supremacy, of this showing that some problem can be run much faster on a quantum computer than a classical one, even just not a useful one. There keeps being this back and forth of whenever that kind of announcement is made by someone, then people try and simulate it classically, and then you kind of keep this race between quantum and classical computers. But we have reached a point now where there are these claims of faster problem solving for certain types of problems on quantum computers that hold up against our best classical computers. And it's also important to note that because of the way that quantum computers scale compared to classical computers, you only need to add a few more qubits to the quantum computer for you to be able to make these problems very difficult to simulate on the classical one. So we kind of reached that milestone as a community with this back and forth with the ever improving classical simulation methods. So let's look at what Google have now announced with this chip of Willow. So this is the blog post, and there are two aspects highlighted. There's the aspect of reducing errors exponentially as they scale with more qubits, and there's the aspect of performing well under this benchmark so that a computation is performed much faster than the best supercomputers can do. So this second point is kind of similar in spirit with what was announced in 2019, in the sense that it's this point of showing that for this problem that quantum computers are particularly suited to, there's a way of doing it much faster on a quantum computer than on a classical one. And so the part of the announcement that has had more attention within the quantum community is really this first part, which is to do with reducing errors, the ability to reduce errors in qubits, and that's a process called quantum error correction. So, to give a bit of context, Google did an experiment showing that they can achieve a certain milestone in this field of quantum error correction. And they posted this onto a preprint server. The paper was put on the preprint server archive a few months ago. And when that was posted, it got lots of attention from the quantum community as a new milestone reached in the field of quantum error correction. And it's a demonstration that's within a family of recent demonstrations that have been shown of various aspects of quantum error correction. There's been lots of interesting progress in this particular area of quantum computing in the last couple of years in terms of experimental demonstrations. But what was exciting in particular about this one is that it brought together lots of pieces that are needed for error correction to work in a way that hadn't been done before. So in each previous demonstration, you could always say, well, they didn't quite show this aspect or this aspect. But this demonstration really brought all the parts needed for quantum error correction together and then showed it kind of all running. So it kind of really demonstrated that this process is possible. So that's the part which got attention from the community a few months ago when this paper was put out. And it was a really focused effort from the Google team to show this experiment. So that was really cool. And I can talk a bit about what that was actually showing. So what it is showing is that there's this problem that we face with quantum computing, that the qubits that we make quantum computers out of are really noisy. So that means that they have lots of errors due to interacting with their environment. And if we try and add more and more qubits and we try and kind of control them and reduce these errors, we can try and squeeze as much juice as we can out of controlling these qubits. But eventually, as we make bigger and bigger quantum computers, the noise is just going to get too much. The errors are going to get worse and worse as we add more qubits to our computer. So we know that we need a process called quantum error correction, which is a way of reducing this noise by encoding one qubit in lots of qubits. And this adds protection by encoding one into lots of, so we say one logical qubit into lots of physical qubits. That then protects that information. So by using a lot more physical qubits, we can encode a few logical qubits, but in such a way that they have fewer errors. And it was shown that this is possible theoretically in the 90s. But even though we can do that, we can do this encoding, which itself is really cool that that's even possible in principle because it involves having to extract the information about errors in qubits without collapsing the actual computational state of the data that we care about and then correcting it, all kind of finding out what these errors are while preserving the computation. So that's really cool in itself, but it's not quite the whole story, because you could imagine that even if you try and do this encoding process, as you bring in more physical noisy qubits, maybe you actually end up bringing in more noise than you're taking away from your correction. So if you're trying to make a better protection by adding more physical qubits, then the noise might actually go up because you've added more noisy qubits. And a really important point in quantum error correction is to reach a point called threshold. So what this means is that when the physical qubits, when you get them below a certain error, then you can actually show that as you bring more noisy qubits in, your error overall goes down. Your error of the logical qubits goes down as you bring in more physical qubits. And so this is a really important point to reach, is getting the errors of the physical qubits below the threshold, and then showing that this quantum error correction process can actually work. So that's what they did in this experiment, is in show this kind of real-time error correction process working in such a way that as you increase the size of the encoding, so increase the number of physical qubits you use for each of your logical qubits, so add more protection to your logical qubits and reduce the errors, that you're actually taking away more error than you're putting in. So that's a really great milestone to reach as a community. And there were times where skeptics of quantum computing would have said that this wouldn't be possible, that you can write it on paper, but in practice, the engineering challenges are going to be too big to be able to actually get this scaling to work. So it's really cool that this demonstration shows that it actually works. So this is what's discussed in this part of the blog, where they talk about getting below threshold and kind of having these increased sized grids of encoding the qubits. So that's the quantum error correction side. And there's another fun comment which was made in this blog, which is interesting in particular to me, since my background is in the foundations of quantum information. I've worked on really thinking about the fundamental aspects of quantum physics and what it tells us about reality. So I thought it was interesting to see this comment about how the fact that we can use quantum computers to efficiently address some problems that we can't do with classical computers in reasonable timescales, it says it lends credence to the notion that quantum computation occurs in many parallel universes, in line with the idea that we live in a multiverse, a prediction first made by David Deutsch. Now, let's unpack this a bit. So, firstly, the idea of quantum mechanics implying many parallel universes was proposed by Hugh Everett, a physicist, and it was proposed in order to try and solve the measurement problem of quantum mechanics, which is essentially, everyone's familiar with Schrödinger's cat, the idea that the cat can be in a superposition of being dead and alive. And so if you apply quantum mechanics to Schrödinger's cat, to macroscopic objects, if you apply quantum mechanics to yourself, I mean, we're made of atoms, so why not? Then what it implies is that when you measure a quantum system that's in superposition, it doesn't just irreversibly collapse to a 0 or a 1. You actually become entangled with the system, which means that together you enter an entangled superposition where one version of you sees 0 and another version of you sees 1. And there's this kind of conflict between thinking that quantum theory applies universally to measurement devices and to people and cats and leads to this emergent multiverse. There's a conflict between that and another interpretation of quantum mechanics which says that a measurement causes an irreversible collapse. So somehow when you measure a quantum system, it irreversibly goes to 0 or 1. And the scientist David Deutsch was trying to come up with a way to test between these two different theories, that measurement causes irreversible collapse and that measurement is fully reversible in its entanglement instead, which leads to this many worlds picture. And it was in thinking about how to test this that he came up with the original idea behind a quantum computer, and that was the precursor to his work in the initial stages of building the theory of quantum computing in 1985. And then when explaining, so if you want to find out more about those thought experiments, I've made some videos when I was working with IBM Quantum. I made some videos on the Qiskit YouTube channel in a quantum paradoxes series, including some going into depth about this experiment for testing many worlds against collapse. So you can have a look at that if you're interested in more details. But the interesting point here is that when thinking about how quantum computing actually works, David Deutsch suggests or says that it's making use of this multiversal structure of reality in order to work. So he asks questions like, okay, so this quantum computer is using all the different parts of the quantum superposition and then interfering them to give the right answer. Where did those processes, that superposition, where did that physically exist? How did that computation, how was there enough capacity for it to physically happen in reality? And so there's an argument that you can put forward that the only way to explain how quantum computing actually can tell you something more efficiently than a classical computer can is that it's making use of the multiverse, in the sense that it's using all these different parts of the superposition, which are the branches of the multiverse, and it's using all those different parts of this quantum multiverse structure in order to give you the outcome of a computation. And that's, I want to say, it's the mainstream view of quantum computing, and neither is the many worlds theory, though it has gained some popularity, I think, in recent years, but it's always hard to tell what the mainstream idea is exactly. But it's interesting. There's this kind of open question about how fundamentally quantum computing actually gives an advantage over classical computing. What's the fundamental resource that it's using? And thinking about these questions provides a very interesting perspective on trying to actually understand physically how is this computer able to do something more efficiently than a classical one? How are the different laws of physics that we're using to explain these kinds of computing actually coming into play here? So it's nice to see a reference to some foundational aspects of quantum computing, which are also where it first came from in this blog. So that's a summary of some aspects of the announcement. Obviously, there's a lot more information in here and lots more context about the field of quantum computing, but in summary, it's exciting progress. It's not yet reached the stage of doing something solving a useful problem faster than a classical computer can. I think we'll know when that happens because whoever does it first will be shouting about it. But it's exciting that we've reached the point of actually demonstrating these milestones towards these large-scale quantum computers, which have the quantum error correction actually working. So I hope that some of that was interesting, and I plan to make more content around different aspects of quantum computing, including on the fundamental side of things as well. So if there's anything you'd particularly like to hear about, then let me know in the comments. Thanks.